Hi everyone, my name is Michalis Papadimitriou. I'm a research fellow with the University of Manchester and I'm working on the TornadoVM project. So today we're going to talk about Java, LLMs, and GPUs, all in one thing. And we're trying to think about ways how we can run inference of LLMs locally on GPUs in just Java. So just a few things about myself. As I mentioned, I work in the University of Manchester. I'm a research fellow. I work in the TornadoVM project. I work on the integrations with machine learning frameworks. And I did similar work previously for a startup that now is part of NVIDIA and for some research labs. If I was giving this talk 3, 4, 5 years ago, 6, because Tornado has been running for a decade now, I would go over I would spend 10 or 15 minutes from the presentation discussing why, as Java developers, we need to have access to GPU. I would go all over discussing about the parallelism, CPU architecture versus GPU architecture, accessibility, portability, how Java code that it's supposed to be write once and run everywhere, it should follow the same concept on GPUs, about how we can integrate different frameworks, and about productivity and all these kind of things. But if one just search for the term GPU in DevVox today, in the talks, they would realize that the GPUs are relevant for the Java community nowadays. So you can see 7 different talks on GPUs that vary from programming GPUs to orchestrating GPU with Kubernetes, everything. So there's no need anymore for motivation, but there is a need to discuss about how we can access, as Java developers, these GPUs that are available everywhere from our laptops, desktops, servers, mobile phones, etc. So for this reason, it's very important that there are 3 different talks about people discussing here how you can access these GPUs. And all these, they have their pros, their cons, and if you have time, look into their videos. So the question is not anymore if we need GPUs for Java, we need GPUs. The question is how we can make it in a seamless way to be accessible with all this kind of ecosystem that Python has been building it for the past decade or so, how we can make seamless integration, but more importantly, how we can build our own libraries. How, as Java developers, utilize the tools, the programming models, and what we have learned, as long as latest advances of the JVM, like Project Llama, for example, or tools like TornadoVM that I'm going to discuss later, to build our own GPU libraries and cut this middleman and this dependency on third-party libraries and native, like, for example, Onyx runtime, GPU backend of Llama C++, etc. So this talks about how we can build a reliable library to run fast inference on GPUs, just in Java. And OK, a hint here, we have built it already. It's open source for the past 4 months now. We have integrated with LLM4j. And because I don't want you to wait, I'm going to show you right now a small example. So here, this is my laptop. On the right-hand side, you can see the monitor of the GPU resources. And this tiny spike here, it was a Java process actually ran on the GPU. And here you can see it's just a Java program that it uses the streaming chat API of LLM4j. Nothing fancy, and passes a prompt, who are you, to an LLM, in this particular case on a Llama 1 billion model. It set up a system prompt, so because we are in Belgium, OK, I wasn't sure about the language, but OK, in that case, I set it to have a hybrid response between French and English. And all this ran in my GPU. That's a tiny example of what you can do with GPULlama and Tornado. But it gives you a hint of what's coming next in this presentation. So let's go back into my slide. How this project started. So again, it all started from DevVox here in Belgium last year. when Alfonso and Alina gave a presentation about Llama3.java. So how many of you are familiar with the Llama3.java project? OK. So it's a single Java class file that it runs very fast LLM inference for Llama 3 models. So imagine it like a one BRC for LLM inference. It's super fast. It uses Project Panama, Vector API, native image. So it could be, let's say, the holy grail of if you want to do LLM inference in Java. And its performance, it was highly competitive even with the native solution that they run on the CPU. So this project is open source. It's great, and it's even great for educational purposes. So during this talk, Alfonso asked for help. If someone can take it from there and try to see how it's going to work if you enable GPU acceleration in it, and ask for us, the TornadoVM team, if we can do that. So we got that challenge. We implemented GPULlama, and lately we have extended it also to be compliant with the LangChain4j. So on the latest release, we are a model provider. But let's see how we did that. So the project is open source. It's called GPULlama3.java. And you can find it here in this repo. And if we want to explain it in these bullets, GPULlama3 is an example of how you can build GPU-ready AI libraries in pure Java. So it's just a Java project. It's an extension of Llama 3. So we reused many of the components like the tokenizer, the model importer, the sampler, things that they make sense that you can do it in Java, you can do it on the CPU side of things. And we did what we know to do as a TornadoVM team, and we extended it with a GPU backend. So we use a TornadoVM. We got all the mathematical equations that were important for this LLM model, and we create the library inside with its own packaging, individual components, that you can understand what really runs on the GPU. And we extended it also for a different set of models. So now, instead of running only Llama 3, you can run Llama 3, Mistral, 5.3, Qwen 2.5, Qwen 3. Gemma is almost ready. And you can have interoperability between a Llama 3.java backend and the Tornado backend. And keep that information, because at the end of this presentation, I have a very interesting demo for you. And also, it has been integrated with LangChain4j, as I mentioned. But why we're doing all that is, if you have used LangChain4j, usually it looks something like this, that you're setting up requests on LLMs that are running on servers. But if you have something that latency is important, or you want to have your data on premise, this is not always the case. So, and maybe latency is the thing why you start thinking why you need to run things in premise. So if you keep, let's say, your own the same setup and try to run things locally with your LangChain4j application, most likely you have the option to switch between two different, let's say, execution engines. Either it's going to be all Llama or the Onyx runtime, which is great. But again, it's wrappers, it's native code, and you're adding one more dependency on your project. However, partially this problem has been solved with not only the Llama 3 project, but also with the JLama, that both of them, they are complementary, and they boil down to the same ideas. They use Vector API, Project Panama to have very fast CPU inference engine. Llama 3 has support for the native image, and JLama, for example, has support for a larger, let's say, selection of models. And also they support the quantization through emulation and on byte arrays. Again, this solves partially the problem on the run CPU, but it doesn't solve the problem on performance. And if you want to make things run faster on-premise, through this approach, you need to rely, again, on all Llama or Onyx runtime and their GPU backends. That, for us, most of the time is a black box. We cannot really understand what's happening underneath. We cannot have fine-grained access to the model itself, or we need to use something like the Onyx Java bindings and these kind of things. And we try to solve that problem and make this use of GPUs for LLM inference as seamless as possible, and to do it in a way that it can be extended in the way of the need. So if someone takes GPULlama and see how we have encoded the models that we support, it can be easily extended for a different set of models, or they can experiment with an experimental, let's say, inference architecture. And I'm going to show you the exact code a bit later. But we need to think about how we can do this, let's say, GPU inference in Java. But before doing that, we need to understand why we need that. And I already mentioned a few of the reasons to do that. We need to reduce the dependencies on third-party frameworks, reduce the dependencies on native code, to reduce the language interoperability between Java and C++ through all these approaches that are available, easier deployment for on-premise machines, but to iterate faster. But more critically, to be able to keep Java competitive in the AI ecosystem, adopt, create our own tools, and maintain them in the open source without relying to third-party libraries. I think this is the most important drive for our work here. We know the requirements now. We have a reason why we're doing that, but we need to do, as a team, we did a sanity check. Does it make sense to spend all this effort and build this library? So we looked into the LLM architecture, into its purest version, its maths, and we know that GPUs are great for linear algebra, and pretty much transformer architecture is just a sequence of linear algebra equations. And the most fundamental thing that you can find in a transformer architecture is this matrix, vector matrix multiplication. And it's crucial that it's matrix vector multiplication because it's make it things a bit trickier to squeeze performance of GPUs out of it. And keep that in mind for later on. So this matrix multiplication, if we want to just write it in Java, it would look something like this. So we're going to have some float arrays, a read-only array that contains the weights, that usually what is trained the model upon, and we're going to have a loop that iterates and calculates a dot product, and finally we're going to return the result. And each LLM model has many of them, and each of vector matrix multiplication here, it's very important because this W, it means the weights, and the weights are very large read-only data that make the inference of the transformer a bottleneck. So we did an experiment, and we got the Llama 3, and we tried to profile it for just let's say 1 billion parameters. And we would see that 9% of the time we spend it in these mathematical equations that I just showed you, and most of them indeed are these matrix vector multiplications. So indeed, it was a very good candidate to try to accelerate with Tornado. So how we can make that faster? TornadoVM, it's been out for almost a decade now. So it was a bit ahead of its time, let's say. We had a deep dive on Monday that we went all through its API, how you can use Tornado, how you can program, how you can debug. It's been open source. We had plenty of examples, README, API, Docker images for NVIDIA, Intel. Yes, and if you want to really look into Tornado and look into this presentation. So as I mentioned, TornadoVM has been growing for a decade now, and it has a very mature ecosystem that help us build GPULlama and some other projects. So for example, the European Space Agency uses Tornado to accelerate the simulations because they have a very big code base that they do analytics for the space in Java. So they use Tornado to accelerate their computations, and they have some interesting results of reducing some simulations from 30 days to just 5. But as I mentioned, Tornado has a very mature ecosystem. So it's just a plugin. So it's just a library for any JDK distribution that you are using, even if it's OpenJDK, GraalVM, Mandrel, Zulu, whatever. And it supports OpenCL, CUDA, SPIR-V, and now we're about to release a Metal backend just for the Apple Silicon. And also because it's based in Graal, and the compiler of TornadoVM is based in Graal, we can run any of the Truffle languages. So if you have something that is JavaScript, Ruby, R, Python, you can run it through Truffle on Tornado. But it was more important for us that we have a rich ecosystem of tools. So we have the Tornado visualizer, which helps visualizing the execution engine of Tornado. We have Pulse, which is our own profiler, that is just an intermediate layer of profiling the GPU. So you can use JVisual, the integrated profiler of TLJ to profile your application. And when you start doing things on the hardware, you can use the Tornado Pulse to visualize the behavior of the device. We have a plugin for IntelliJ, which is called Insight. So it can help you with the programming model of Tornado. So when you are running a Tornado program, it's going to give you hints about if you are trying to do some objects that they have dynamic allocations or anything that is not valid to compile it for the GPU. And we have integrated to use proprietary tools like NVIDIA Insight. And one last thing, we're about to move our LTS to JDK 25. So we are always trying to keep up with the latest LTS version out there. So all this ecosystem help us to shape the needs for this library. So now let's revisit that matrix multiplication example that matrix vector multiplication example that we've seen. So again, it looks very simple. We have two loops that they iterate to calculate the dot product of the matrix vector. And if we want to translate it to Tornado code, it's going to look something like this, not more complicated than this. We see that the primitive float arrays, they convert to float arrays, that the Tornado float arrays under the hood, they use Project Panama to store data of the heap through arenas. And this is more convenient for us to send and receive data between the heterogeneous device. We see that the only change that we convert the float arrays to the primitive float array to the Tornado float array. We have constructor from primitive arrays, from segments, from byte buffers, from everything. And we have annotated that the outer loop is parallel. So we gave the compiler a hint that it's a parallel loop. So when you're going to try to offload this method on the to the Tornado stack through the Tornado task graph API, our compiler is going to try to parallelize it. If it cannot parallelize it, if you have done something that is not correct or is not valid, it's going to give you the appropriate exception. So this way, it's what we call loosely parallel semantics. And you can express things that can be very easily parallelizable. And it's very easy for you to getting started with how the code looks like. But in the case of LLM, we had to go a bit further and use the other API of Tornado, which is called kernel context API. So the kernel context API allows you from the Java side of things to program like a GPU engineer. So it exposes through an API all this kind of constructs that you are going to find in CUDA, OpenCL, SPIR-V, Metal. So it exposes this kind of things like group ID, local ID, which is the global thread ID, the local thread ID, things like allocate local memory, expose it to the caches on the core of the device. We have barriers. And here what you can see is that a very optimized matrix vector multiplication that has also a reduction inside. So combining these two parallel models, programming models for Tornado, allow us to create the final library. So at this point, I want to switch to my terminal. I'm going to go to the Tornado, and I'm going to run an example. So here, I'm running this matrix vector multiply that we are discussing from the beginning with two different APIs and pure Java. As we can see, we set up some default values that they're reflecting to the values that we can see in LLMs of medium size, let's say 1 billion parameters, 3 billion parameters. We had 140 iterations just to benchmark the Java side of things. And we got this performance metrics. And as we can see, when we use the kernel context API and we run through Tornado on our GPU, this spike there, we're about 100 times faster than Java. Okay. But also, what is important is that kernel API between the parallel API is 7 times faster for us. And we got that information to build the whole, let's say, GPULlama. So now that we have all the components available, we have ways to program the mathematics, let's say, of the inference. We have Tornado, we have a way to interact with the GPU completely from Java. We got Llama3 and we started extending it in a way to work with Tornado. This is a very, very high-level overview of the GPULlama3, and the brown parts are what is standard in every LLM inference. We have tokenizer, model provider for its model, a sampler, but we have a Java inference core for every of the model. So if you open the source code of the GPULlama3, you are going to see an inference core for Qwen, Mistral, Phi, Gemma, Llama3, that it utilizes Project Panama Vector API to run fast inference through Java. And for the GPU side of things, we have the other package that has the layer planner, the compute kernels, and the master plan. These three components allows you to plug and play different models into the GPULlama. The compute kernels is just selection for all these mathematical equations, and it looks like this. So if one looks into this class, they could see that this matrix vector that we discussed already, some reductions, some silos, some adjacent place, and some more advanced things that I'm gonna show you a bit later. But this is just a collection of all these equations put together. So our next step, it was to see how we can break down the algorithm into Tornado. And Tornado offers this task API. So for each individual component on the left-hand side that reflects into the mathematics of the LLM inference, we created a Tornado task. And that way help us also to adapt to other model providers. So each equation of the left-hand side reflects to a task on the right-hand side. So as you can see, QKV are three matrix vector multiplications, QMatMul, KMatMul, VMatMul, they correspond to this. Then we have the multi-headed attention, which for us is a parallel attention and reflects to a method that's called process heads in parallel. Then we have the residual, the post-RMS layer normalization, which is what we call reduction to one block FFN, etc. So for us, it was very easy afterwards to iterate and add. When we had the Llama3 in place, it was very easy for us to add more models very, very fast. So the initial implementation took us months, but then just porting another model is just a week's work to have it working on CPU and GPU. In what we're particularly interested here to see the power of Tornado and how sophisticated things you can do is that this task that's called Fuse FFN W1, W3. And why is it important for us? And why is it important for us? Because if I open my IntelliJ and go to that specific method, so layer planner, yes, you would see that it looks like this. So this task here, this method here, expresses, even if it doesn't look like, expresses a very sophisticated GPU optimization. So it combines multiple things together. But because it's difficult to dig into it, let's summarize them here. So it does multiple things. So it operates on half-float point arrays, which directly map into FP16 types onto the GPU. It does two matrix vector multiplications on the weight matrix W1 and on the weight matrix W3. And then it does a silo activation, which is a multiplication. And finally, it does another multiplication and stores the result only from the thread 0 to the global memory. So this generates a very efficient GPU code. That's how we managed to get so fast GPULlama, to make it to run so fast on GPUs, by getting concepts that are available for GPU programmers and just code them in pure Java with the Tornado API. And it's just one-to-one mapping. A few optimizations that we got, they're available in frameworks like MLX, Llama C++. They have backends for different OpenCL codes, and it was just one-to-one mapping for us. We didn't have to extend our compiler. It was mature enough to handle them. OK, so I'm done with the boring slides. So let's see what's happening. So I'm going to run here GPULlama, and I have prepared the script to explain to you what's happening. So now I'm running on this local machine, which is my laptop, four different models of different sizes onto my GPU. As you can see that they run through the GPULlama. Then on the bottom right, it's cut, but we can see Java processes running on GPU. And there we can see that first we run a Llama3, now we run a QM3 model of 4 gigabytes, 1.7 billion parameters. Now we run a Phi 3 mini of 7 gigabytes. We see the spikes. Tornado takes care, it's a virtual machine on its own, takes care of allocations, deallocation, how the data management happens from the CPU to GPU, how your program interacts with the GPU. So you don't have to do anything explicit. Tornado is going to free the resources. It's going to run the inference, and if you're not needed, it's going to free the resources. It's going to manage. So it looks like this. And you see that this is just the GPU in my laptop, which is NVIDIA 5090. It runs all the different models from different vendors. Now we can see that we are trying to run a Llama 3 8 billion in FP16 precision. All this just through the GPULlama project. And if you have worked with Llama 3 before, it's the same thing. So you just pass the model. It doesn't need any special sauce. And so just to run something, it looks like okay. So yeah, this is how it looks like. So you just pass an arg file with the options. You have the model that you want to pass. Then either if it's instruct once, or if it's an interactive mode. Let's try something different. So I can do here just as interactive, and I'm going to increase the number of tokens to 1048. So now the time that it takes here is the time that it takes for GPULlama. Sorry. The time that it takes here is the time that it takes for GPULlama to load your model, to JIT compile into OpenCL, and copy your weights onto the device. So once this initialization process is ready, then your model is ready to run inference. So this process, you only have to do it once. So now, as you can see, I have an 8 billion model. You can see the spikes there, because the 8 billion model is, I think, 16 gigabytes. So I had to copy in 60 gigabytes onto the GPU. So now the model is ready to run inference. Who are you? And you can see that the inference runs there. And write a vector add in C. So now we see that we utilize about 65% of the GPU that on my laptop. It runs the inference. It might stop because of the context. But OK, this is how it looks. And then if we exit the process, Tornado is going to free the resources. So you see that this spike went down. Now, we can examine also our application in different ways. So what we can do, we can go here and say, Llama, Tornado, I want to run on the GPU, OpenCL backend. I want to pass a model. Let's pass from the models a bit high, 1 billion parameter to be a bit fast. OK. Sorry, prompt. Tell me a joke. But I would like to see what's happening underneath. So I would say verbose init. Now you see that it loads the model to FP16. That's how much time it took for the Tornado to create its execution plan. So it means the task graph. How much time it took to compile our Java code into GPU code. And how much time it took to transfer the read-only weights onto the device. And then that was the initialization process. Then the model is hot, the GPU Llama is hot, you can run inference. And let's see what is this JIT compilation. The JIT compilation is that if I put print kernel, you could see that Tornado underneath generates all these OpenCL kernels for all the tasks that we've seen. So if you try to dynamically load the different model, you're going to go through the initialization process again. The Tornado is going to go through another layer planners, and it's going to generate the new OpenCL code. Same thing if you run it through PTX or SPV, because it supports multiple backends. So imagine that if you have an Intel GPU, you can even run it there through SPV. And the code generation is going to work the same. And you can do some other analysis also, and use the integrated profiler of Tornado and say profiler, and get some more fine granularity about the different tasks. OK, here we directly profile the hardware events from the GPU driver. So this is the hardware events that takes to launch the kernel, to execute the kernel, to copy in the data, to copy out the data, and to compile it. But OK, as you can imagine, because here we have 16 layers times 300 tokens times 10 tasks, this is very difficult to visualize it. So that's why we created this tool, which is called Pulse. And it digests the profiling logs of Tornado. And here we can see how it looks like. So it digests these JSON entries that we've seen in the terminal, and it profiles each individual task graph. So we have one task graph per model layer. So you see this uniform behavior here. And for us, it's a validation that the inference engine behaves as we expect. Because each layer performs the same tasks. We have the same distribution, so we don't have anything. Only the last one, which is expected, because it's logics that calculates the final probability for the token. And it goes through a very large weight. So it is expected to be so slow. And also, we can zoom in and see the individual tasks. Here is the W1, W3 that I discussed before, that it has two different matrix multiplications and two multiplications together, stacked together. So it's like combining 4 different bars into one. And we can have this interaction with the device. Also here we can see the task distribution. Okay, logic is 10%, which makes sense for these models. And we can see how much time it spent to copy in the read-only weights during the warm-up phase, how much time we're taking for us to copy out the token. So this is the probability for the last token. And we can do this kind of analysis here. Now I want to switch gears, and I want to talk about the LangChain4j integration. And as I mentioned, GPULlama is ready, is integrated with LangChain4j, 17.1 release. And we have a repository with all with examples, with some simple examples like chat model, streaming chat model APIs, but also had some time and we implemented some of the agentic examples. So we have the CV reviewer and the TikTok running locally through the GPULlama. And we have we did some performance analysis on it. Let's see how the API looks. So how many of you have used LangChain4j before? Okay, we have implemented the chat model API and streaming chat model API, like the other model providers. So inside you can find a GPULlama3 chat model builder. You pass temperature, top K, top P, max tokens, whatever. And the only fancy thing is this tiny on GPU that you have to set up in true, and you have to have Tornado installed in your system. So it's going to automatically run the inference of the model on your system. You don't have to do anything else. If it's false, it's going to go through the llama3.java path. So it's going to give you the llama3.java performance for you. Nothing else. Just install Tornado, use a LangChain version of 1.7 plus, and this is it. Also, you can follow the link with examples to see what it does. But I promise there's no special sauce in it. And let's go back into that example to show you what's going on. So, okay, let me open BitTop. Okay, because we are gonna need that. And again, let me rerun the streaming. Oh, sorry. So this is the streaming chat model example that I showed you in the very beginning. But OK, this is simply prompts. Let's do something more interesting. So during the break, I had an idea. So I got the agentic example of a TikTok. And what I did is that I went here and I created one chat model that uses a large model of 8 billion parameters that I'm intended to run on the GPU, and one chat model of 1 billion parameters, which is smaller, and it's going to run on the CPU through Llama3. And the idea is that to have these agents collaboratively play TikTok here on my laptop. So in my own machine, I can utilize the CPU and GPU all in Java. So let's hope that it's going to work. Okay. Yeah, TikTok game. Yes. Before running it, on the right-hand side, you can see BitTop. On the top is the CPU utilization. On the bottom is the GPU utilization. Let's run it. And as long as we wait to load, again, we can see that this is the pure LangChain chat model API. If I open the constructors, I'm passing an 8 billion model. Here I pass 1 billion model parameters. The one is going to run on the GPU, the other one on the CPU. Yes, and they start playing together. So if you look into these lines, you can see that CPU utilization goes up when the CPU player plays. GPU utilization goes up when the GPU utilization when the player on the GPU plays. You can imagine with the agentic library, you can start doing these kind of things, and you can do asynchronously and having one agent trying to do inference on something big that makes sense to run on the GPU, while you have a smaller agent running on the CPU. through the Llama 3. All in Java, the CPU engines in Java, the GPU engines in Java. Okay, okay, things they don't go as expected, but okay, it's a POC. But you get the idea. So okay, let's forget the left-hand side and just see the utilization. So CPU and GPU collaborating on playing this game through the agentic API. And yes, if you have any other examples that you potentially can be useful or any other models that they can be collaborate for something, let me know. I'll open a pull request in the repo, and I'm going to be happy to test it in any of our setups. Yes, so I was planning to show you the CV reviewer, but I thought that this is fancier, even if it didn't go as expected. But we ran the CV reviewer, the agentic example, and we had some interesting benchmarks. So we got from the agents example the CV reviewer. We have implement to run with the GPULlama3 and with the TornadoVM backend on this machine, on this laptop, nothing fancy. And we tested different models that they were able to perform the review of the CV and produce something valuable. And we tried Llama 8 billion in FP16, Qwen 3 in 8 billion FP16, and Mistral 7 billion in FP16. So we tried, okay, the simple example, chat model, stream example, an example with chat memory, and the CV reviewer. And we see that just by going to GPULlama and run all things locally through our system, if you use the CPU backend, the Llama 3, if you use the GPU backend, you are consistently 3 times faster, at least for Llama and Qwen 3. I think the Mistral outperforms in this kind of tasks because it didn't meant to do this kind of tasks. But we can see that we can get up to, let's say, 4 times faster inference on our local machine, on our local development machine. And soon, as we have the Metal backend released, this is going to reflect also on M-Silicon performance. So you can imagine that you can start doing things in premise on CPU, GPU, and directly through the GPULlama have access to the source code and understand what is running under the hood. What is next for us? Looking into AOT execution, also for Tornado, but also for the GPULlama. And what is going to land in our TornadoVM and GPULlama next week is we have extended support for quantized types. So quantized types is something that we miss from the JVM, but they're on the GPU. And if we want to be compliant with the GPU, we need to find a way to express this reduced precision that is important for performance. So in Tornado, we have extended Tornado API that uses the memory segments to express quantized types like int8. So we are going to extend GPULlama and with int8 types. So we're going to be able to load natively int8 models, Q8 models, for example, and run them much faster in the GPU because now we have to dequantize Q8 models to FP16. So we're kind of doing this emulation to run quantized models on the GPU. The other thing that we're exploring for the next month is that, do you remember this big bar on the inference that is a bottleneck for us, the performance? We are going to connect Tornado with NVIDIA libraries directly. So if we do this analysis through Pulse and our tools, that we have a task that is a bottleneck and we cannot optimize it further, we are going to hook in directly to cuDNN from NVIDIA and offload it there. So you are going to be able to have this different, let's say, hybrid of execution, also for different vendors. And finally, we have a pull request open to integrate with the Quarkus LangChain4j that we didn't manage to finalize it for this presentation, but this is what we're going to plan to do next. And if you have any use cases or if you have any examples that can be useful, feel free to contact us through discussions, pull requests, and we're going to be happy to implement it or guide you through. Again, thank you for your attention. Here you can find the links for Tornado, GPULlama3. I don't remember if I mentioned it that Tornado and GPULlama have Docker images because NVIDIA has its own Docker images passed through. So you can have Docker images for both of them and run them there. And the final link is that all these examples that I ran with the agents and the simple exams, there are everything there. So what you've seen running, you can try to replicate it on your setup and see if it works. So thank you. If you have any questions.
Yeah, what about JLama? Are you also thinking to have a JLama integration?
No, because we did that with Llama 3. So the main difference with JLama and Llama 3 is that JLama had a very much larger collection of models to support. So we refactor Llama 3 and we have integrated Llama 3 in our GPU Llama 3, and we extend that. So we have our own, let's say, classes to extend for models. If you have any specific model in mind that you want to write, just write us an issue and we are going to extend it. But we have a CPU engine that is pure in Llama, the Llama 3. It works great for us. It has native image support, so we can have in that, but yes. So it's just model coverage. So, yeah. Yes? Not for inference, not for the inference, but Tornado can do that. So from the Tornado API, it has an API that it's called concurrent device. So imagine you can create two task graphs with Tornado and enable the concurrent devices. If they don't have dependencies together, Tornado is going to schedule it on your device. So if you have a system with a GPU and an integrated GPU, you can have two Tornado tasks to run in parallel on both, but we haven't yet went to the parallel inference. There's one-to-one mapping with the algorithms and the maths. So if you open the library, the compute kernel library that we have, and if you saw the layer planner, for example, if you open the algorithm, the layer planner in the library, there's a one-to-one mapping going from the maths to the GPU code. So if this is the question, there is no special source in between. Yeah. Yes?
Is there a path to upstreaming TornadoVM or maybe some of its components to OpenJDK?
For that, there's Project Babylon. That they are working on that, and yes.
But I think TornadoVM has different optimizations.
TornadoVM relies on Graal, and well, I don't have time now to show you, but it does very aggressive optimization. So when it's going from what you've seen in the API, there are many things that you get for free when you're generating GPU code. We are replacing intrinsics with intrinsics that are for GPUs, like FMAs, local memory, vectorization, the DP4A, what you've seen here. So the DP4A, it's a special instruction that does the dot product on int types for the GPU. So Tornado has all these special optimizations baked in through the Graal compiler, and ensures that you can have so fast inference. Yes. Yes?
Dependencies are there. You showed like this library that you have to link to, but how you get access to the hardware? What does this mean?
Yes. So to replicate the example that I had for the Devox demo repo, you just import lang7for-j, the version that used Tornado, that has integrated the GPU Llama. That's the only dependency there. And the other dependency that you have to have configured in your system CUDA and OpenCL, which is just the driver, and install Tornado. So the only dependency is to install Tornado in your system. Yes. Yes. Or you can use the Docker images that. Yeah.
So from what I understand, Babylon is basically generating C code or CUDA code, which then requires the native tool chains to generate the native code for the accelerator, for the GPU. So does your GRA compiler directly generate the native code for the GPU? You don't require any native tool chains or compilers?
We generate directly OpenCL code, and in the case of CUDA, we generate PTX code, which is the intermediate representation. So you still need the driver to compile the source code to the binary. Yes?
Have you benchmarked it against, let's say, local inference engines like Llama?
We haven't done that because it wouldn't be a fair comparison. We have benchmarked it only against the Llama3.java at this point. Because we try to benchmark it as a pure, let's say, Java engine and not a GPU engine. Yeah, but we're going to do it, yes.
So the follow-up is, okay, why is it not a fair comparison? Because like most of us, I assume, feel like
Because you should expect that if we can hook the native library, it should be about, let's say, 70% of the performance, roughly. But for us, I think the main drive for this is the language interoperability. So not to have this kind of dependency to native things. Because now you can do everything just in Java, and you don't have to have a dependency to native or to Llama C++. And
I guess what we're saying is like there is no way to go faster than
no, there's no way. No. No, there's no way to for example, to go faster than these inference libraries, yeah, for sure. Because what they are doing is that if you open any kind of the backend of these libraries, it's thousands of lines CL files that they have if-defs, and they have highly manually optimized OpenCL code for all the different permutations. So when you see mixed precision, FP16, int8, they have manually written this kind of optimization. So in theory, you could express many of these kind of things with Tornado. So the API and the compiler can handle it. Because what I showed you back there, it was CL files that are kernels that can be, let's say, 500 lines of code that they do this kind of optimization. But it depends. If it's something performance critical, and that's why I mentioned the European Space Agency, they use Tornado. And Tornado has an infrastructure that's called pre-built API, which allows you to hook in files written by hand, like CL files, PTX files. So you can have this kind of chain of tasks, and intermediate tasks, if it's something that is performance crucial for your application, you can use this pre-built API and load something that you have manually written, and it's super specialized for the algorithm that you use. So that's why I mentioned that it's quite mature, and it has all this kind of tooling that it can cater your needs. Yes. Yes, thank you very much.